Hi, Miles. We'll get started here shortly. Hi, everyone. We'll get started here in a few. Sorry about that, everyone. My internet just went out on me just for a moment. Uh, so looks like I'm back up and functioning, and hopefully it'll stay that way. So I'm gonna go ahead and share my screen. Uh, just a moment. I forgot I got booted out, so I need to go back in. All right, I think I got it now. Okay. All right, so can somebody give me a heads up, thumbs up? I mean, if you are seeing my the course homepage.
Yes.
Thank you very much, Miles. Okay, so let me go into the weekly over. Well, I'll start with the announcements because I did make a few. I do apologize about getting my um, times mixed up again. I'm not used to teaching a 5:30 in the evening class online, and I was thinking that I had my standard 3:30 class during the like spring and fall semester, and I was kind of panicking because I was stuck in a meeting. But thankfully, I worked it all out correctly in my head and figured out that wait a minute, you have class at 5:30 today, not 3:30. So sorry about the alarm there, but hopefully I didn't cause anybody any major issues in you know getting the times mixed up. So the other important things that I want to cover is number one, the midterm exam is open, and we'll take a look at that just in just a moment to clarify the instructions, make sure everybody understands what's going on there. Number two, I did put out a video that talks about the scoring and writing of the project summary. Uh, I want to cover some of that material with you, but it is going to have to wait until next week because if you've looked at this week's overview, you can see we're kind of booked solid in terms of the overviews that I need to get through this week. And next week, the material is fairly straightforward. In fact, next week will be perfect for me to talk about the project because actually, um, the astronomy overview you work through on your own, and the waves overview is fairly straightforward. I can do it in definitely in one class period. So I'll have time next week to really go in more detail about the project. But any event that you're wanting to go ahead and get involved in the writing, this video talks about the writing and the scoring. And so when I cover the project information next week, I'm pretty much going to say what's on the video. So, you have access to that to go ahead and get started with the writing. The other thing that I will tell you is that if you look under the project link under assignments and activities on the left side, that's the quickest way to get to the project information because once you click that link, it's right there. These picture templates, please take a look at them because a lot of students watch the video or they follow along when I cover the information, but then they don't go and use these picture templates to kind of help guide them on the layout for the actual summary. So you want to definitely include these templates in um, your review of the project materials. So if you choose to watch the video that I put in the announcements, please don't overlook these picture templates. Okay, so other than that, I'll come back to the project and talk about it in more detail next week. All right, so let me do first things first, midterm week overview. Okay, so this is where you get access to the information on the midterm exam. Okay. So let me click on the logistics and then I'll talk about that along with the study guide, so on and so forth. So 11:59 p.m. Saturday, the 3rd of July is the deadline for getting the midterm exam completed. You have 2 hours unless you have some other type of accommodations, which, you know, that's an individual thing. But by and large, you have for the bulk of the class, you'll have 2 hours to complete the exam. Um, when you go into the actual exam, you need to type the work in the exam space provided. You must show your work. I don't give credit if work is not shown. And you follow the instructions included with the problem. If there's anything specific about a question, the instructions will direct you accordingly. Um, do not email any work to me. Okay. The exam is completed entirely in the quiz space. All work is to be included there. It's worth 100 points, and the point values are indicated with each question. And what I do is, after the exam closes, I'll grade the exams. I try to include comments to let you know, what you might have missed on a particular question. Uh, it usually takes me about a week to get it done, but this is a smaller class than I typically teach, so I may be able to get it done faster. It just depends. Um, you have to complete this exam on time. If you miss the exam, then you're going to have something, you know, official to document your, um, you know, missing the exam and needing a makeup. So, you know, I just give some examples here of a doctor's excuse, an obituary, a judge's order. There, if you had to work extra with your employer and you have some type of documentation to show that, I have used that on some occasions. But I handle that exam makeup situation on a case by case basis. So, you know, you will have to substantiate why you missed the exam and need a makeup. Okay. So that's the logistics of the exam. Could you please unmute and ask any questions that you might have regarding the logistics? All right. So the other thing that I made available to you is a study guide. So the whole idea of this study guide is for you to get some exposure to the content, additional exposure, practice with the content that we've covered up to this point. So the scientific method, nature of science, measurement, units and unit conversions, 1D motion, vectors, projectile motion, uniform circular motion. So all of the topics that we covered prior to Newton's laws. I know that we covered Newton's laws and gravitation last week, but as I mentioned, those topics are not on the midterm. Just these topic areas listed here on the study guide. Now, I do my study guide a little bit different than maybe what you've been used to in the form of a study guide. And that is because I don't give you a set of questions or problems to answer to prepare you for the exam. What you do is you make up your own set of questions and problems related to these topic areas. Now, how do you go about doing that? How do you go about creating your own study guide? So you we'll have to consult other resources beyond what we've dealt with in my notes or in the resources in each overview. So you can use other books, you can use other internet sites or any other credible sources. If you have a question or doubt about whether a source is credible, feel free to reach out to me. But under useful links, I have given you access to some other sources that you might consult to formulate a list of concept facts and sample problems. What I want you to do for your study guide, to build your own study guide, is to compile a list of 10 concept facts related to these topics and solve 10 problems related to these topics. Now, what you don't want to do is have all of your concepts or all of your problems related to one topic area and neglect the others. By the same token, I'm not telling you that you have to have 10 concept facts and 10 problems for each topic, but at a minimum, you should have 10 concept facts and solve 10 problems related to all of these topics. Okay, so a total of 20 items at a minimum, 10 concept facts, and 10 problems. If there are examples that I've worked in my lecture notes or in my extra notes that I made available to you, the extra notes are available in the announcements. Remember, you cannot use those either. Okay, so you truly have to go find your own stuff related to these topic areas and build a set of study items. In the process of finding and compiling these items, you should be paying attention to what you're putting together so that you're actually reviewing the content. Okay. So when you have that study guide built, you can email it to me just like you do with any other assignment. And it is worth 10 bonus points toward the midterm. Okay. So find sources of your choice and use those sources to put together 10 concept facts and solve 10 problems related to these topic areas, which are represented on the midterm exam. Any questions about the study guide? Just feel free to unmute, ask your question. Okay. All right. That's the study guide. Now, the actual midterm exam, if you click, it is open and available to you now. So I'll just do this right quick. I'll switch to student view because I always like to verify that what I'm saying is exactly true here. So yes, there are, the midterm exam is open and available. It opened Saturday actually. And I did mention last week that if you wanted to get started, you definitely could do so. When you open that introductory page, all you have to do is take the quiz and make sure you type your work, not just your answers, your work and your answer in the space provided. Okay. So you have until this Saturday to get that done. Any questions about the actual exam? If you're paying attention, the way I got to the exam was in the weekly overview. When I'm in the exam midterm overview, I just clicked on this link, midterm exam. Also, you might have noticed that it does show up in your to-do list on the home page. You can definitely access it that way as well. Okay. So without any questions, I'll just go ahead and move into the momentum. I'm going to do my best to try to get through the momentum and work overviews today. Whatever I don't finish, I'll tackle that along with the thermodynamics overview. Um, and then, as I mentioned, next week we'll resume with these other two overviews, and I will go back and talk about the project for you. Okay. So this week we're going to be looking at momentum. Um, so momentum is a very useful property of a moving object. It tells us something about how much motion the object possesses. And since our job is to analyze motion or quantitatively describe a moving object, momentum is one of those properties that we often utilize. And we'll look at the circumstances, that require or necessitate us using momentum. And we'll also be looking at momentum's counterpart, impulse. And we'll see, what are they? We'll learn how to calculate them. And then we'll look at the law of conservation of momentum as it pertains to um, moving objects, and in particular, collisions. And so, along with that, we'll look at how we can utilize, we can solve problems with momentum conservation, and also we'll look at how we solve problems using the momentum impulse theorem. So, those are the kinds of things that you need to be able to do and understand as a result of going through this material. So you have a set of activities on your plate regarding this topic, this overview. You have a discussion that you have to complete by Saturday. Your second bonus, I'll talk about in just a moment. You have problem set number 8. Remember, problem set number 8 will deal with gravitation from last week, right? Because that's our wrap up of the material, doing a problem set on it. Okay. So these items are due by Saturday. You have access to some materials to help you with that. Chapter 7 in your textbook, which I've made available here, deals with the momentum. I have some videos that deal with momentum. And I have access to a simulator here that deals with momentum. Those of you in lab class, this is the same simulator that you're going to be using to complete the experiment on momentum. And then these are my notes. I'll come back and get into those in just a moment. I do want to spend just a few talking about your second bonus, okay? So this second bonus is what I like to call my flexible bonus, in that you can decide where you want to use the points, meaning you can add the bonus points from this assignment to any area of your choice except for the project and overall course score. So you can take these 10 bonus points if you complete the activity successfully. You can take the 10 bonus points and add them to your midterm score along with the other bonus that you have, the first bonus on satellite motion, right? You could hold these 10 bonus points and put it toward your final exam if you choose to. You can take the points and split them up and add it to problem sets or discussions. However you like to use those 10 bonus points, except you cannot use it on the project or your overall course grade or score. So what you have to do is you have to build a car. It says that'll travel as far as possible, and it says at least 3 meters. The idea here is that the car has to move. Okay. Otherwise, it's just a nice, pretty thing you built, has nothing to do with motion, because if it doesn't move, I mean, it's like having a car at your house. If it doesn't move, it's not much of a car. All right. So these are the materials that you're allowed to use to build a car. The scissors are for cutting. They're not actually part of the car. And I always have to specify that, because for some reason, I always have a few students who want to use the scissors as part of their car construction. And I'm thinking, well, that wasn't what I had in mind. So, you know, use the scissors to cut these materials. But other than that, they're just, one of those things you need to have access to. Tape, plastic lids. These are like drink cup lids or something comparable. Skewers. These are like what you use to put like shish kebab on your grill, you know. But you should use plastic or wood. You shouldn't use metal. Okay. Straws. There's regular straws. One balloon and one tray. Now this tray can be and like a tray that would have like a dinner that you would put in the oven, or like a tray like the styrofoam that when you go in the store and you purchase meat, and the meat is on this like styrofoam looking tray. It might be pink or yellow or white. You can use that. Just make sure you sanitize it. I don't want you working with something that's potentially um, germ filled. Uh, or it could be a cardboard tray. I always tell students, if you have a question about whether your materials are acceptable, just shoot me an email, show me a picture or something to that effect, and I can tell you, yeah, you can use it. Because if you violate this materials list, I won't accept your work. Okay. So you need to build this car using these materials. You also need to include a write-up that explains how each of Newton's laws, which we studied last week, applies to the motion of the car. Now, the gravitation law is not part of this. Newton's three laws of motion. Okay. So the write-up has to explain how each of Newton's laws applies to the motion of the car that you build. Um, I'll go back and add to this right here that when you send me your items for the bonus, you have to send me the write-up and at least a picture, preferably a video of the car in motion, right? I mean, I don't have that here. I'll go back and add it. I didn't think I needed to until I started getting students who said, well, you didn't ask me for a picture of the car or a video of the car. And I'm thinking, how is someone going to know if you built it if you don't send me a picture, right? So build this car. It has to be mobile. It has to move. And you have to have the write-up on Newton's laws as it pertains to the car, and a picture or video of the car that you build, right? Are there any questions about this particular bonus? All right. So this bonus is due also by Saturday. And I do apologize. Yes, I'm sorry.
This sounds fun.
Yeah. Yeah. I try to make this I mean, I try to liven it up when I can. I mean, I know physical science is not, cool or always fun, especially in this virtual environment where we're not in a laboratory setting or dealing with each other face to face. So, you get to play around a little bit here. Okay. Um, so again, this is due Saturday as well. I know it's piling up, but remember we're in an 8-week format, and I've got to take you through the entire course just like I would any other, for any other class. All right. So with that being said, I think I can get into the momentum notes. All right. So here is the definition of linear momentum. The reason it says linear momentum is because we're looking at objects that have straight line motion. Now that straight line motion could be one-dimensional or two-dimensional, but what we are not referring to is rotation. So objects can rotate while they're moving. We're not talking about that type of momentum, okay? So the way we get an object's linear momentum is we multiply its mass times its velocity. Be careful there. We said mass times velocity, not mass times speed, okay? So two objects could have the same mass, the same speed, but if they move in opposite directions, they have different velocity and therefore different momentum. Momentum is a vector, so direction matters. So two objects, same mass, moving with the same speed, but going opposite directions. For example, one going east and one going west, they do not have the same momentum because their direction is different. Okay? So I always tell students, momentum gets its vectorness from velocity. Since velocity is a vector, momentum is a vector, okay? So the reason I distinguished the momentum that we utilize as linear momentum, because a lot of times you hear momentum, though it just referred to as momentum, but be clear, even though it doesn't, if you see it referred to as simply momentum, they're still talking about linear momentum and not rotational momentum or angular momentum. We don't study angular momentum in this class. So everything you deal with is going to be based on linear momentum, okay? And in fact, we don't even study two-dimensional linear momentum. We only look at momentum in one direction, one-dimensional linear momentum, okay? So we try to keep it simple because it's an introductory course. And also to study two-dimensional momentum, just like two-dimensional motion, we need trig. And so we're not going there. We keep it all simple at this introductory stage. Okay. Now, the other thing is that even though the idea of knowing what momentum is and how we calculate it is new, linear momentum is actually connected to something that we've studied, and that is Newton's second law. So we can actually take Newton's second law and express it in terms of linear momentum. And in particular, we can express Newton's second law in terms of the change in momentum over the change in time. So there's a direct relationship between momentum change, or delta P, over delta T. Remember that delta symbol means change. So if we look at how the momentum changes per unit time, then we are looking at an alternate way of expressing the net force. And we know from Newton's second law, the net force is equal to what? Mass times acceleration, okay? And so I won't spend a whole lot of time looking at the derivation of Newton's second law from this change in momentum or vice versa. Just understand that there's a relationship between Newton's second law and the momentum change per unit time. Um, so be mindful. I didn't say momentum, I said momentum change. Okay. Now, since momentum is written as mass times velocity, then the unit for momentum in the SI system is kilogram meters per second. Mass times velocity. So the unit for mass is kilogram. The unit for velocity is meters per second. Okay. So here's an example of a new unit that you're being exposed to for a new property that you're being exposed to. So remember, I told you at the beginning of the course, you want to go get yourself one of those big index cards. And every time we come across a new property, you want to write down what that property is, and you want to write down the SI unit that goes with that property. So here's a new property, momentum, and its unit is kilogram meters per second. Kilograms for mass, meters per second for velocity. Don't mix that up with the unit for net force or force. The unit for force is kilogram meters per second squared. The unit for momentum is kilogram meters per second. Okay? I see that happen a lot. When students see this, kilogram meters per second, they automatically think force. But that's not the case. Okay? Impulse. Impulse is a property that can be obtained by rearranging the Newton's second law here, this version of Newton's second law. So if we multiply both sides by delta t, then we get F net times delta t equals delta p. So we just did a little bit algebra. And out of that comes this relationship, delta p equals F net times delta t. And so this property, impulse, is what we call change in momentum. Impulse is the change in momentum. And remember, this way of looking at change in momentum came right out of Newton's second law. Okay. So impulse is not momentum. Impulse is the change in momentum. Okay. And so what we're looking at here is that the impulse or change in momentum that an object receives is equal to, and here they say average net force, and we'll look at that in just a moment to try to get a handle on why they're saying average net force instead of just net force. We'll look at that in just a moment. We take that average net force and multiply it by the change in time. So you can think of it this way. So for example, if you are a baseball player and you swing in order to, hit the ball, right? That's the whole goal in baseball. You want to swing the bat, hit the ball. So when that bat makes contact with the ball, it imparts an impulse on the ball. And that impulse is derived by looking at the amount of force that is, making contact with the ball. In other words, how much force is being applied to the ball. And then how long is the bat in contact with the ball? So if you want to do a good job of as a batter, you have to have a really good batting technique. And batting technique means that throughout the entire swing of the bat, you maintain contact with the ball. So they call that good follow through. You have good follow through when the bat stays in contact with the ball for the duration of the swing, right? So that is a good follow through because you have a larger contact time and therefore more impulse or change in momentum. And so this equation tells us that, for example, that you can have a large force acting briefly or a small force acting over a much longer time interval and produce, um, you know, a larger impulse. Okay. So, um, when you're playing baseball, for example, you don't always want to hit the ball in the outfield or hit a home run. Sometimes you want to do what's called a bunt hit. And a bunt hit is a short, choppy kind of hit, meaning what? The bat doesn't stay in contact with the ball for very long, but you hit it hard. You hit it hard for a short time period so that it makes a really like almost like a line drive in the infield so that the batter has a chance to run or create an opportunity for another player to steal a base, right? Because while the pitcher, catcher, whoever is scrambling to catch that bunt, get that bunt, the runner has time to take off, right? So that's an example of impulse where you have a short time span, short delta T, but a larger F net. Okay. So that's why they say average effective force, right? So for example, um, you know, while home run hitters typically have, they're power hitters, right? We call them power hitters. But even for those power hitters, they don't hit the ball with the same amount of force every time. So that's why we talk about the idea of the average effective force. Okay. So we kind of look at this force that actually varies over a time interval and just look at the average force that's being utilized to determine the amount of impulse. Okay. Conservation of momentum. So when we say conservation of momentum, or when we use the word conservation in physics, we're not talking about the conservation like, save the whales. Although that is a very important effort, it's not the way we mean conservation in physics. When we use the word conservation, we're talking about the fact that within this closed system, within an isolated system, the momentum remains constant. So when we look at this closed in system where there are no external forces impacting the system, within that closed system, the total amount of momentum remains fixed. Okay. So this idea of conservation is very important in physics because momentum, as we'll see shortly, isn't the only property that's conserved. Okay. So It's important that you understand that for momentum to be conserved, the system has to be isolated, meaning there are no net external forces impacting the system. In other words, when we say conservation, a system is closed off from the outside effects of the environment. Okay. Now that's a bit far-fetched because we know in the real world you can't really isolate things that way. But we're trying to find a way of what? Simplifying this system or modeling a simplified version of the system so that we can get at some key ideas regarding the system. Okay. And so we can say conservation of momentum in term is expressed in terms of the total momentum, which stays constant. The total momentum in this closed system remains constant. So let me give you a simple example that you might be able to relate to, because they talk about the idea of for subatomic particles, and we don't really go there. So if you've ever played pool, um, 8-ball in the corner pocket kind of pool, right? So in that system, you can model it utilizing the idea of momentum being conserved. So one of the key things that you have to do when you play pool is you have to rack all the colorful balls in this triangle. You rack them, you put it on the table, it's stationary, nothing's moving, so nothing has momentum, okay? And then you take this cue ball and you hit it and it starts to move. So it has momentum. And then that cue ball, if you've done a good job, hits the colorful balls and everything scatters on the pool table. All the balls scatter. And so the momentum that was housed in the cue ball is then transferred to all the colorful balls, right? So then everything is moving. Now everything has momentum. If you take the momentum of all of the balls that are moving and you add it up together, you will get the same amount of momentum as what the cue ball had before it hit and broke those colorful balls. So the total amount of momentum in the system is fixed because we're treating the cue ball and all the colorful balls as this isolated system, so that the total momentum in that isolated system is always the same. Okay. So they give the example here of microscopic collisions. And yes, that is definitely a useful concept when studying these subatomic particles. But honestly, we're not going to ever study subatomic particles. So I wanted you to have a real example that you might relate to, kind of, an everyday kind of thing. Although I don't know if you play pool every day, but I think you can get the idea. That's a more relevant example to the kinds of motion that we study. Okay. And so the reason that momentum conservation is important is because it's a useful concept for studying collisions. And you think about it, that's exactly what's happening on the pool table. You got lots of collisions taking place. And in particular on the pool table, those collisions are elastic. And so you can utilize this momentum conservation to study collisions. And so one type of collision, like what happens on the pool table, are elastic collisions. And so elastic collision, kinetic energy is conserved, and we'll see what is kinetic energy in just a moment. But whatever it is conserved. We know what that means. The total amount is fixed. Momentum is conserved. and the objects bounce off of each other. So that is exactly what's happening on the pool table, right? You have these balls colliding with each other, but they don't stick together on a pool table. They actually rebound off of each other. And so that's an example of an elastic collision, okay? So again, we're not interested from the perspective of a subatomic particles, but um, what we are saying is that because we want to analyze this system from a perspective of no friction involved, then we can say those elastic collisions that take place on the pool table are isolated. And so momentum, kinetic energy are both conserved, and the objects are bouncing off of each other all over the pool table. Okay. And what we do is we only focus on one dimension. And so you can see that's happening there on a frictionless surface. The reason we have to have it be frictionless, not frictionless, frictionless, is because remember the net force has to be 0. If you have friction, that's not going to happen. So you see this like oval shaped line that's drawn around is saying that these things are isolated. And so you have this object M1 that's going to bump into M2. Well, that's what a collision is, right? Literally things bumping into each other. All right. And so when they collide, they bounce off of each other. And you see in this case, they're going in opposite directions, right? And so the momentum total is the same. So the total amount of momentum in the system before the collision is equal to the total amount of momentum in the system after the collision. Okay. Now, fortunately for you, we don't really get into the math of this type of collision because it's a little bit complicated, because you also have to use the idea that kinetic energy is conserved, and the math is a little bit challenging. So we won't go there in terms of the math for this elastic collision. But the one we will get into a bit is for the inelastic collision. So for the inelastic collision, the difference is that kinetic energy is not conserved. So momentum is still conserved in this inelastic collision. Kinetic energy is not conserved. And for the types of inelastic collisions that we want to analyze, the perfectly inelastic collision, the objects stick together. Okay. So we have these perfectly inelastic collisions where the objects will collide and stick together. And so momentum is conserved, but kinetic energy is not conserved. And so to analyze an inelastic collision in one dimension, here we are again, these two objects, they're coming toward each other head on. They're going to collide. The system is frictionless so that we know we're dealing with this momentum being conserved. And so after the collision, you can see here.
Is it like a magnet with
those
the
are not magnets. Those are not magnets. Those are two objects sliding on a frictionless surface, like two blocks sliding on ice. And they hit each other and they stick together. In this case of an inelastic collision. But if this was an elastic collision, they just bounce off of each other. Okay. And so now, the thing we have to be mindful of here is that after the collision, these objects are stuck together. And so if they're stuck together after the collision, they will move together. Well, that's logical, right? If things are stuck together, they're going to move together. that also means that after the collision, they will have the same velocity. Well, if things are stuck together, they move together with the same velocity. That makes sense. You can't be stuck to something and move with a different velocity than it does, or else you're not stuck to it. Okay? That scenario of the objects sticking together after the collision is what allows us to analyze their motion. Okay? Now, the last thing here that they talk about are these reaction type systems. We're not going there. Yes, this is the start of rocket science. Well, actually, Newton's laws was the start of rocket science. We don't have to worry about these type reaction systems. These systems are systems where the mass of the system is changing. Well, that's a little bit above our pay grade at this point. We don't want to analyze systems where the mass is changing at this point. That math gets a little bit complicated. In fact, you need a little bit calculus to really do it justice. So we're not going there. But just understand that we are dealing with systems or analyzing systems where the mass is constant. But there are systems that we deal with where the mass is not constant. And so we call those reaction type systems. And a rocket is an example of that because of its thrust, the thrust that it experiences as it expels gases when it's lifting, right? When it lifts off, the exhaust represents fuel that's being burnt, right? And if the rocket is using fuel, then it means its mass is decreasing, which allows it to have a higher acceleration, right? So it's rocket science and we're not going there. Okay. So that's what I wanted to cover with you on momentum. I'll try to make sure I have a moment on Wednesday to look at an example problem or two. But I want to kind of go ahead and start dealing with kinetic energy, with energy, so that, at least have a chance to put some material on the table for you. And so, we're going to be looking at energy, various types of energy. We're going to look at conservation of energy. We'll look at work and its connection to energy. And we'll look at the idea of some systems where energy is conserved and where energy is not conserved. So I'll do as much as I can today, and then we'll finish this and go to thermodynamics on Wednesday. All right. So you do have some items for this that are due by Saturday. That's problem set number 9 and your energy discussion. Okay. There are 2 chapters in your textbook that deal with energy. That's chapter 2 and chapter 8. And you should go into those and take a look at those, read those, review that material along with these energy videos. So I'm going to go into my notes here, which are the supplemental energy and work notes. Okay. All right. So the first major idea that's being presented here is that work and energy in physics are very different compared to the way we use the words every day. For example, if we say work, people will say, I went to work, work was easy, but they're not using the word work in the way we do in physics. Okay, work every day might mean whatever job you go to from 9 to 5. Okay, or whatever you do at that job from 9 to 5. None of which might be equivalent to the physics definition of work. So we have to be careful that we give when we're using these concepts and words and properties in physics, we have to be sure that we're distinguishing from the everyday definition. Okay. So we, you know, that we have to adhere to the rigorous definition of energy and work, and make sure that we understand how to calculate and utilize them for physics process purposes. And so what we need to see is get a handle on are the different types of energy, and the idea that they're interchangeable to one degree or another. And, you know, that's a pretty important understanding of our environment that physicists and scientists have, you know, gathered information on and have an understanding of, because number one, I like to approach motion from the perspective of work and energy because they're scalars. Okay, they're scalars. Remember, scalars don't involve a direction. So we can put aside all that force and momentum business that deals with vectors and look at a much simpler way of analyzing motion from a work and energy perspective. But we have to know how to properly calculate it and understand what we mean when we say work and energy in the physics world, okay? So to find work, we take the magnitude of our force and the magnitude of the displacement, and we multiply them. So see, by just taking the magnitude, all we're worried about is the number part, right? We're not worried about the direction part. But there is a stipulation that we have to adhere to, and that is that our force and displacement have to be in the same direction. I'm not saying we're using the direction. I'm saying they have to be in the same direction in order for work to be done. So let me give you an example. So imagine that there is a box sitting on your table and you push that box. The force that you apply to that box has to be in the same direction as the box moves. You push the box, it moves. The force that you apply and the displacement that the box experiences have to be in the same direction. Well, you might ask the question, well, how in the world could I apply a force to an object, or a force be applied to an object, and the force and the displacement are not in the same direction? Two scenarios. First scenario, friction could be applied to the box. Remember, friction exists because the box is touching the table, right? So friction is being applied to the box while it's moving. But that friction, remember, opposes motion. So if the box is moving to the left, for example, friction is to the right. Well, friction is definitely a force that's being applied to the box, but the displacement is in the opposite direction. Remember, the box is moving to the left, but friction is being applied to the right. So friction force to the right, displacement to the left, those are in opposite directions. So work is being done in that case, but that work is negative in the sense of, you know, they're not both in the same direction, but they're in opposite directions. Okay. We don't worry about calculating work as it pertains to friction, because that whole idea of the opposite direction, to really do it justice, you need to understand a little what we say vector mathematics, and we're not going to go there. Okay. So then, if that's not the scenario that we want, where the force and the displacement are in different directions, what case do we want where there is a force being applied, there is a displacement, but there is no work being done? And that is to carry an object, or in this case, carry the box. So think about it. If you're carrying an object, you have to be supporting the object's weight. So gravity wants to pull the object down for sure, but because you are supporting the object, you are applying a force against the object's weight. So the force that you are providing would be pointing up because you're supporting the weight of the box. But which direction is the box moving? Is the box moving up? No. Is the box moving down? No, because you're supporting the weight. The box is moving forward because you're carrying it. You're supporting the weight, but walking forward. So the box is moving forward. But the force you're applying is up. So think about it. If the force is up, the box is moving forward, the force and the displacement are actually perpendicular to each other. So when you carry an object, the force and the displacement are perpendicular, meaning they're not in the same direction. So no work is being done. So think about it this way. When you go into that fancy restaurant and the waiter is carrying a tray with 10 different dishes on it, technically, he's not doing any work because he's carrying the tray. If he wanted to do work in the physics sense, he should push the tray. So there, in that example, explains to you the difference between our everyday definition of work and the physics definition of work. Because the waiter will surely want to get paid for carrying around trays all day, even though technically in the physics world, he or she is not doing any work. Okay? So anytime your force and your displacement are perpendicular, as in carrying an object, no work is being done. I think it's obvious to look at the equation and see if there's no force, no work is being done. If there's no displacement, no work is being done. So if you push against a wall, you are applying a force to the wall, but the wall isn't moving, so no work is done. That's a simple example. Okay? If you apply a force to an object like the box sitting on the table and it moves, your force and your displacement are in the same direction, work is being done. Carry that same box around, no work is being done because the force and the displacement are perpendicular. Okay? I'm stressing this because in order to understand energy, you need to understand work because they are related and in many instances interchangeable. All right. So now here we have another property, work. We use the capital letter W for work. Please do not mix this capital letter W up with the capital letter W used for weight. This work W is measured in joules. So here we have a new property, work, and we have a new unit in our metric system, the joule. And you see the way we break down a joule is 1 joule equals 1 Newton meter. 1 Newton times 1 meter, right? 1 Newton meter. The Newton comes from force, the meter comes from the displacement. We put them together, we get a joule, okay? So again, work is a very important property because it allows us, well, to understand energy as well because they're interchangeable. So here is a property which relates, a theorem, excuse me, that relates work and energy. It's called the work energy theorem, okay? And this theorem says that the net amount of work done on an object or system changes its kinetic energy. So if you do work on a system, the system, let me say that again. If you do net work on a system, net, remember that word means what? Unbalanced or extra work. This work is not being canceled out in some way. So if you do net work on a system, its kinetic energy is going to change. Okay. So one way we know that an object has absorbed energy is because its kinetic energy will change. Now, they didn't formally define kinetic energy for you, but kinetic energy is energy related to motion. So if we change the object's motion, we change its kinetic energy, work is done. Okay? How do we calculate the kinetic energy? This energy associated with motion. That's what kinetic energy is, energy of motion. If we change, how do we measure that kinetic energy? Excuse me. 1/2 mass times velocity squared. Kinetic energy, 1/2 times mass times velocity squared. Okay? So you notice what they're finding here in this equation is the change in kinetic energy, delta KE. A lot of times you'll see kinetic energy abbreviated as KE. So delta KE is what they're finding on the right side of the equation. How do we know? Because they're taking the final kinetic energy or the kinetic energy at some later point minus the kinetic energy at the start. Okay? So if we take the difference between the final and initial kinetic energy, we know how much work was done. Okay? Gravitational potential energy. So the reason it's called gravitational potential energy is because in this instance, we're doing work on an object against gravity. So if you lift an object, for example, gravity wants to pull the object down. You're lifting the object up. So you're moving the object against gravity. When you do that work on the object against gravity, why? Because you are applying a force to the object. You can't lift an object unless you apply a force. So you lift the object moves, so work is done. In this case, the work that's being done is against gravity, so the object stores energy, and we call that stored energy gravitational potential energy. Okay? And so a lot of times you'll see the gravitational potential energy denoted as PE with a little subscript G on it, gravitational potential energy. Okay? And so it tells you here that if you lift an object to a height h, the object will gain potential energy because it will gain height. So the amount of potential energy that it gains, or the change in potential energy for that object, is equal to mgh, mass times gravity times height. So just by looking at that formula or equation, we know that we're not dealing with systems where the mass is changing. And remember, mass is the same no matter where you go because it's location independent. But gravity can change. So for example, if you go to the moon has less gravity than the Earth. Okay? So even if you, let's say for example, you lifted an object for 10 meters on the Earth and 10 meters on the moon, because gravity is less on the moon, the object will store less gravitational potential energy. Okay? The other thing, obviously, in this equation is height. So you can change the amount of potential energy that's stored by changing an object's height. Okay? So they give you a visual here of storing and releasing gravitational potential energy. So what they're doing is they're taking this object that has it's like a clock with a bob on a chain. And what they're doing is they're pulling the chain so that the bob goes up. Well, as that bob goes up and moving through a height h, it stores up gravitational potential energy, but in the process, work is done. Because remember, work is force times distance. Well, how much force do you have to apply to lift the object? Is weight. How do we determine its weight? Mass times gravity. And so that's the force we apply, mg, the object's weight, and we're moving it through a displacement, height h. Okay, because if we pull the bob down through a displacement d, it is going to experience that same displacement up, right? We pull a chain down through a certain displacement, the bob has to rise up that same displacement, or the height h in this case. So the work done is going to be equivalent to mgh. Well, hey, that work done is the same amount of potential energy that's stored. So you can see in this instance that the work done is equal to the change in gravitational potential energy. Likewise, if you let go of the chain and the bob starts to fall, then it will release that energy, mgh. So pulling the chain down through a certain height, h, stores up energy, mgh. Let the chain go, the bob falls, releasing the same amount of energy that is stored, mgh. Okay? You think of it this way. As the object rises, it stores gravitational potential energy. As it falls, it releases that gravitational potential energy. So that brings us to the idea of conservative systems. And I'll just be the last point that I make today. We'll pick up here and continue forward on Wednesday. I'll try to get a few examples in dealing with momentum and some with energy on Wednesday. So when we looked at that system for the clock just a moment ago, where you store up energy and release it, we're dealing with an example of a conservative system. So a conservative system is one for which there are conservative forces involved in affecting the motion. Okay, so a conservative force is one for which the work depends only on the starting endpoints of the motion, not the path taken. So think about lifting an object against gravity. You want the object to end up at a certain height. You could lift the object straight up to that height, or you could carry the object up a set of stairs or an incline up to that same height. Or you might move from start to finish, from start to the height in some type of loop-de-loop path. The idea for a conservative force is that it doesn't matter how the object gets to the height h. The path that it takes is not relevant, only the starting and ending points of the motion. Okay? So in a conservative system, the force that is doing the work is conservative. So when you're dealing with these conservative systems, we typically talk about mechanical energy. And that is, you can think of mechanical as motion, energy associated with motion. And so in that particular case, the types of energy that we're interested in are kinetic and potential energy. Okay. And when we focus on kinetic and potential energy, we can say that the total amount is constant in the system. But this conservative system where the forces are causing the energy of the system to change in a way that the mechanical energy is conserved or constant. Okay? And so you see that Ke plus Pe equals constant is an expression of conservation of energy. All right? And so when we look at our system, because the mechanical energy, the kinetic plus the potential energy is conserved, at any point we can say that the amount of kinetic energy plus potential energy that we started with has to equal to the amount of kinetic energy plus potential energy that we finish with. The total mechanical energy at the start is equal to the total mechanical energy at the end or at the final. Okay? And that is because we're dealing with conservative forces like gravity. Okay? All right. So I'm going to end here. We'll pick up on Wednesday, talk about the idea of non-conservative forces. We'll look at a couple of examples that deal with momentum, work, and energy. And then we'll go ahead and talk about thermodynamics. Okay? So we have a few more slides to get through. And then, we have a few more slides to get through where work and energy are concerned. And then we'll finish up by looking at the thermodynamics. Okay. So if you have questions, I don't have class until 7. I can hang around for a few more minutes. I'll be happy to answer any questions that you might have. Just unmute and feel free to ask your question. Okay. So I'll stop sharing, but I don't see any questions popping up in the chat. Okay. So I think that means we're good, right? And I'll see you back here on Wednesday.
Definitely doing homework. A lot of
Homework?
us.
Yeah, question about a homework?
So I'll definitely be doing homework.
Oh yeah, because like I told you before, we're starting to get into the area now where You know, that practice and that diligence about reading, watching the videos is critical, right? Because if you don't interact with this material, you won't learn it.
Yeah, you're right.
Yeah. Okay. So we'll be back here on Wednesday. I look forward to seeing you back here on Wednesday. Y'all take care.